Thank you. So let me write local algorithms for block models or for community detections. And what I'm going to talk about is a little bit related to the title, but not just. The plan is I'm going to talk about an interesting phase transitions, which is new, or haven't been studied before, phase transitions for broadcasting on tree. Then I am going to talk about two overly optimistic predictions from physics. And the two overly optimistic predictions from physics, one of them will be a sort of a soft introductions to these local algorithms, which I'm going to define. And the other one, the reason I will introduce this overly optimistic prediction is it's going to be a sort of a nice introduction, if we have time at the end, to talk about, I think, a nice question about deterministic counting in the context of the block model. And everything that I'm going to talk about, if I haven't really planned the time, but the work that I'm going to talk about is based on a number of papers. The first one is with Niemann and Sly. A couple of works with Jiaming Su, who is supposed to be here, but is probably interviewing for a job somewhere. So the paper with Jiaming Su. And then finally, it's going to be based on discussion with Lenka and a little bit with Nike-san. So this is the plan. Okay. And as you've seen, since I'm also teaching 2.5 courses this semester, I haven't planned a very polished presentation, so feel free to interrupt and ask questions if you want at any point. So what is the broadcasting on tree problems that we're going to study? So many of you know this process. I'll just draw the picture. I won't define it. The classical process formally. So we have some tree, and the tree is going to be labeled by pluses or minus. And the idea is that in each edge, we have a binary symmetric channel, so it's 1 minus epsilon, epsilon, 1 minus epsilon. So that's the classical broadcasting on tree problem. The new caveat for this broadcasting on tree problem is that we're going to consider the following situation. So, new variant, and I'm going to give some example of this variant. We're going to consider the following situation. So there are going to be the following probabilities. So there's going to be Pn, which is the probability that the optimal estimator of the root, which we know how to compute as a computational problem, is equal to the actual root given, so this is the expected value of the probability that the estimator is equal to the root given level n, which I'm going to write like that, and some possibly additional information. There's going to be Qn, which is going to be, again, the expected value of the probability that this is true, but instead of giving this information I, we are going to give some noisy information of what's happening at the nth level of the tree. So let me give you some examples of this, right? So usually in this, if you haven't seen this board,
with respect to what exactly?
So the process is random in many ways. The tree is going to be random. The probabilities or the broadcast, everything is going to be random. So there's going to be some expectation on the probability. And I'm going to give some examples. So maybe this will make it more concrete in a second. But maybe before I do that, any question before I do that? The usual process is you run this process for a while, and you see what's happening at level n, and you want to recover what's happening in the root. Here the question that we want to ask. So the question, when is it true that the noisy information give you the same quality as information as the non-noisy? Okay, so that's what we want to understand, right? So there's the noisy version and the non-noisy version, and usually, often in the reconstruction problem, we just want to do better than random. Here, it's not that I want to do better than random. I want to do exactly the same in the situation where the information is noisy, as in the case where the situation is not noisy. So let's look at, I'm going to look at 3 examples. So example number 1, so let me tell you what the tree is going to be a Poisson D random tree. So each node has a Poisson number of children with probability with mean D. And I have to tell you what are the other parameters in this case. So I'm actually not going to give you any additional information. So let me just write it I is equal to the empty set. So there's no additional information in what I'm going to give you. Sigma n is just sigma n. What is sigma prime n? Sigma prime at level n. So at each v, the probability that sigma prime nv is equal to sigma nv is going to be equal to half plus delta, where delta is greater than 0 independently. So this means that instead of actually giving you the information at the nth level, I'm giving you a very noisy version of the information at the nth level. As delta goes to 0, it's becoming more and more noisy. Okay? Question that we want to ask here, the actual formulation that we have here. So let's call this sigma prime n with a delta. So we want to know, is it true that as delta goes to 0, as n goes to infinity, this qn, which now I write with delta, is equal to the limit as n goes to infinity of Pn. So is it true that no matter how noisy the information is at the nth level, the answer, the posterior probability is going to be the same if I give you the actual information or the noisy information? Very good? Okay, so this is a workshop about phase transition, so I want to give you some example. Example number 2.
Every edge has the same...
Every edge is the same model, which is 1 minus epsilon epsilon. It's all going to be just this model in this talk. Example number 2 is going to be a different example. Here what's going to be, so T is still going to be Poisson D. Now sigma prime is going to be trivial. I'm actually not going to give you any information about what's happening at the nth level for the noisy version, but I am going to give you some information about I. Welcome, Yuval. Please choose a seat. I am going to give you some information about the nodes, and the information about the nodes that I'm going to give you is for every node, the probability that IW is equal to sigma W is again going to be equal to some number, maybe half plus alpha. And now this is not just for the leaves, this is for all W up to level n. So this model is we call reconstruction with side information. So what happens is that it's not that I give you the labels at the bottom. I actually give you noisy labels everywhere. So I give you, this is maybe a plus, this is maybe a minus, and so on and so forth. In one model, I give you additionally all the information at level n. In the other model, I give you the same noisy information here, but here I give you nothing. There's no information. Okay, so you get information about every node of the tree, but on the leaves, in one case you get the full information, in the other one you get no information. And maybe the last example. Question? Okay. No? This we call side information. And maybe the last example is what we call degree correlated. And what we're going to have here is we are going to have, the tree is actually going to be more complicated. It's going to be a multi-type branching process. Let me write it this way. It's going to be Poisson A from type 1 to type 1, Poisson C from type 2 to type 2, and then Poisson B otherwise. The information will be the tree. Why is the information in the tree useful? Because the two different types have different degrees. If I tell you what's the shape of the tree, you learn something about the value of the nodes, right? So that's going to be the information. And again, in one case, we are going to look at that the information at level n is going to be everything, and in the noisy case, I'm going to give you nothing. Okay, so these are three cases, three examples of models where I want to know how much does the accurate information on the leaves actually help me in reconstructing the value of the root.
So here there's no channel.
And the channel is the same channel. I mean, somehow...
In number 3, it just doesn't play a role at all.
You don't give anything in number 3.
Right, so let me, sorry, I didn't make the mapping very clear, right? So if you choose the parameter A, B, and C correctly, then the conditional probability that from A you go to A versus from A to go to B is going to be 1 minus epsilon versus epsilon. Okay? So here the question if you're a plus or minus is exactly the question if you're type 1 or type 2. And when I give you sigma n, it means that at the boundary of the tree, so let's do this maybe as an example. Thank you for asking. So maybe, so this is going to be a type plus, and type minus, I don't know, and so on and so forth. It says some so there's different distribution of pluses and minus. Maybe minuses have fewer minus children. But at level n, I can either tell you which one is a plus or a minus, which of the two types, or I can just say I'm not giving you this information. So these are the three models for possible information that I can give you at the boundary of the tree. Questions about this? Okay, so this is just so far completely unmotivated. The goal was for those of you who want to take a nap after lunch to do so, right? So the motivation will come in a little bit. But let's first of all see what do we know about these three cases, and then I'll try to relate it to the other topics that I mentioned. So what do we know about the three cases? So example 1. So the classical phase transition for this problem is this paper of EKPS, which says that if d times 1 minus 2 epsilon square is less than 1, you cannot do anything. So if you cannot do anything, you can also not do anything if I give you noisy information. So obviously, so Pn is equal, or the limit of Pn and the limit of Qn is equal to 1/2. So that's not so interesting. Okay, so that's not very interesting. In the other direction, we know that if it's bigger than 1, and then this limit is bigger than 1/2. But all we can prove in this paper with Niemann and Sly is that for large enough C, if d times 1 minus 2 epsilon square is bigger than some constant C, then again you have this behavior. Okay, so this is a situation where you do get some non-trivial information, and you get exactly the same quality of estimate at the root if you have the noisy information as the non-noisy information. So that's an example of the result that you can prove. So that's an example number 1. Tell you the result in example number 2. So this is with Jiaming. So in example number 2, so we know it under various conditions. We know it again if d times 1 minus 2 epsilon square is bigger than 1. If d times 1 minus 2 epsilon is less than 1, or if alpha is large enough. Let me just write alpha bigger than 0.4. That's not the actual number, but under all of these conditions, we know that the noisy information, you don't actually need information at the boundary. It's enough for you to look at the information inside the tree. What do we know about example number 3? So here, actually, all we know is what happens in what's called the density evolution limit. So I won't tell you what it is. Density evolution limit. In other words, it means when A, B, and C go to infinity in the right way, then we know that limit Pn is always equal to limit n to infinity Qn. Okay, so in all of these cases, we know that's the the limits are the same. And there's sort of an obvious natural question that's come for this specific channel. So the question maybe is it always true? maybe in all of these variants you don't need any conditions. We don't have any indication that you need any conditions on the channel, on the parameters of the channel for this conclusion to hold, for the noisy and the non-noisy reconstruction probabilities to be exactly the same.
Sorry, Elchanan, is alpha a measure of how different the two degrees are in the degree correlated case?
In degree correlated case, there's no alpha.
Sorry. What is alpha again?
Alpha is in the side information case, and it tells you how strong is the side information. So if the side information is really strong, then you're fine.
Right. And then what can you say about the degree correlated case?
So in the degree correlated case, we can only deal in the case where A, B, and C are going to infinity in the right way, with the density evolution limit, and then we know that it's true in that case, always.
So clarify, in the second line there, when you say, so there's, the limits are the same, but they're not a half, right?
Right, so very good, thank you very much. I mean, one of the interesting features of example number 2 and 3 for those of us who've looked at reconstruction in trees is that even in the trivial case, the limit is not 1/2. It's a random limit because I get some random information about what's happening at the root, what's happening close to the root. So actually calculating what is the shape of the limit, so it's something that both Yuval and Chris and Lenka and all the experts in the room are aware of. It's an interesting random limit which we don't really understand. But we do understand that under this condition, this random limit with the information at the boundary is equal to the random limit without the information at the boundary.
You take the expectation.
Second?
The expectation, so why is random? Didn't you take expectation?
I take expectation everywhere, hopefully, yeah.
So what's random?
No, the expectation is a number, but for a specific instantiation of the model, unlike the situation right in the case where there's no side information, we know that if the epsilon is large enough, this is going to be 1/2, 1/2. In the side information models, or with the degree correlated models, it's not going to be 1/2, 1/2. Because the instance contains some information. It tells you, even if you just look at the root, in the side information, I tell you, the root is more likely to be plus than minus. So you already know something about the root, in example number 2.
But you are taking your expectation.
That's without the expectation. But if I ask, what's the... So, I mean, look, the quantity that I'm looking at is not the magnetization. The quantity that I'm looking at is the probability that the estimate of the root, given what I'm seeing, is equal to the actual value.
Aren't you taking expectation over everything?
I'm taking expectation over everything, but this quantity in model 2 and 3 is always going to be bigger than 1/2.
But it's just a number.
It's just a number which is always bigger than 1/2.
There's nothing random.
Yeah, there's nothing number about this number, but we don't understand this number. And the reason we don't understand this number is that per instance, there is random fluctuations in the local information that you get.
Yeah, so basically, there's a confusion between if you're also taking an expectation over the information or not.
Yeah, of course, I am taking expectation over the information. This is expectation over everything. Yeah. Thank you for the clarifying questions. Okay, so why do I care about this? Why do I care? So those of you who want to wake up from your nap, why? Yeah.
When you say implies and then you have a quotation mark, it implies, I just want,
Except the 1/2.
it implies only the first thing.
Yeah, this is just the first thing, and this is in this joint work with Neiman and Sly, we have the second thing.
I mean, since you put just quotation mark, it looks like you're quoting the whole first equation, but you're only quoting the first equality.
Just the top one, not the bottom one.
The half on the end. When
In
you
the
reduce
top,
it.
you're only quoting the first equality, not the second, when you go to the next line.
He means ditto mark.
Sorry,
So the limit is not a half. So the limit
This
is not a half.
implies,
this limit is a half.
in the first case, but not in the
Oh, sorry. Thank you. Okay, yeah. That would be boring if it would be 1/2. Thank you for the clarification. Good, excellent. Okay, good. So I keep you awake by making mistakes, which wasn't my intention, but you do what you have to do. Okay, so why? So the question that you should ask yourself now is, or even before, why? Why are you doing this? This sounds like a very technical, some variant of a problem that people studied. Why would you want to do it? So it's a good question. I'm not sure I have an answer to this question. But let me just say what is the connection to the block model. So for this, I have to, should I tell you what's the block model, or everybody knows what's the block model? Who wants to see what the block model? I'm actually sick and tired of the block model. Okay, whatever, block model. Okay, so there are going to be three variants of the block model, corresponding to 1, 2, 3 over there, and 1, 2, 3 over there. There's going to be three variants of the block model. The first variant of the block model is going to be the following. There are going to be n over 2 vertices here. There are going to be n over 2 vertices here. And I'm going to connect two vertices. I'm going to connect two vertices in the same cluster. I have to do the translation in my head, sorry that I didn't prepare it in advance, with probability d times 1 minus 2 epsilon over n. And I'm going to connect two guys in different clusters with probability 2 epsilon over n. Maybe d times 1 minus epsilon over n. Connect two guys in different clusters with probability d epsilon over n. Okay, that's how I'm going to, this is my random graph. So it's what's called a non-homogeneous random graph. There are two different probabilities. There's these two clusters which have probability d inside them, edge probability d times 1 minus epsilon over n, and there's a different probability between the two clusters. Can you see what I'm writing, Martin?
Just wonder why they appear to be both labeled the same.
So so that was my suspicion. So this is d times 1 minus epsilon over n, and between the edge probability is d epsilon over n. Okay. So these are the two probabilities, and so that's maybe that's the model that I'm looking at. And the basic question here, it's a question that started with a very nice paper of Dessel and Lenka and Chris and Zhang and Robert. And Robert. Okay? It's you? Were you on the paper? I forgot. Okay. Florent? It was the following question. You look at this model and you somehow want to recover something about this partition. So ask the following question: when can you approximately recover And for those of you who haven't seen it, those of you who have seen it know it, the point is that I'm giving you this graph without telling you these vertices are on the left and these vertices are on the right. And I'm just giving you an instance of the graph, and I'm asking you, can you tell me a little bit about what's on the left and what's on the right? So that's the question that you have here. And they have an amazing conjecture, which was true and beautiful, and many of us worked on it, which is that the threshold is the threshold. And this conjecture is true, and many of us worked on proving it. They also had a comment in the paper, so this is one place where they were too greedy. They said you can do it with belief propagation, which is actually also true, with order 1 iterations. This brings us to local algorithms, because if you look at order 1 iterations, what it means is that it means, at least in the case where epsilon is bigger than 1/2, where you don't have to normalize the magnetization, what it means is that this decision, if this vertex belongs to the cluster or not, should just be a local algorithm of the neighborhood in the same sense of under lecture. Okay, so let me maybe a comment here. What is a local algorithm? So a local algorithm is an algorithm. I'm looking at really local from the vertices of the graph to 0, 1. And maybe there's also IID uniforms UW for W in the vertex set. And the algorithm at the point V is just an algorithm of the neighborhood of radius R around V, and also of all the uniforms that are in this ball. So I don't think they thought too seriously about this claim. I think this was probably the result of numerical simulation. It wasn't some very deep insight.
Just always forget logs in physics.
Yeah, so it's maybe because maybe it's just Lenka claims that this is the physics notation of the big O, and I'm happy to accept it. But still it raises the question. I don't think you guys thought about it very seriously, but I think it still raises the question: what can you do with local algorithms in this kind of problems? And one thing that should be obvious, I'm just going to do with my hands like this, it's clear that local algorithm cannot do anything in this problem, right? Why can't the local algorithm do anything in this problem? Because I look at my neighborhood, I look at James' neighborhood. Well, I may be more energetic because I'm giving a talk, and James is a little less because he had lunch. But what I see around me is a branching process that looks Poisson tree. What he looks around him is a Poisson tree. We are far away. There are no random variables that communicate between us. There's no way for us to make this separation in a reasonable way. So here everything was correct except this, sort of maybe numerical or, log n emission. So here you cannot do anything with local algorithms. So local algorithms don't work. Then you still ask why. So why did Alan and Joe and I worked pretty hard in order to prove this result? So what we proved is BP, with all the one iteration, we showed this is not true, but the claim was that it's optimal. So with Joe and Alan, we proved the following theorem. So if you start from something better than random, and then apply belief propagation, which is a local algorithm, then you recover optimal fraction. So what does it mean? So it means that many of us worked very hard to find an algorithm under this conjecture threshold, which is correct, that does a little better than 1/2, 1/2. Now we look at this complicated proof that gives you a little better than 1/2, 1/2. And we assume that this is not just bigger than 1, it's actually bigger than C. We take this algorithm, we initialize with this algorithm and apply belief propagation, then you get a better result. And in fact, this result is the best result that any algorithm can get information theoretically.
So what happens with BP? It converges to the marginals?
No, you cannot. I mean, there isn't really a meaning of a marginal here. But you can ask information theoretically among all algorithms, what's the maximum fraction of nodes that you can recover correctly?
Why isn't there a meaning of the marginal, at least for pairs?
So for pairs, there's marginal, but that's. I mean, pairs doesn't immediately translate to the question of identifying correctly in terms of fraction of number of nodes. Okay, so let me state it in the way.
One BP and then.
So I start from an algorithm that's very smart ideas using non-backtracking random walks and so on and so forth. It gives me something that does 0.5500001. So this gives me an estimate of every node in the graph. And then I'm cheating, but this is not an actual algorithm that we analyze. But one thing that you can do is you look at every node, look at all the nodes that are a distance 1 million from it, run belief propagation given this noisy information, and recover the value of that node. So the picture that you have in mind is that you have. This is your node. You have the algorithm that does a little better than 1/2. You look at the values over here, which are not correct. They're very noisy. And then you apply belief propagation, which is just the posterior probability that this is what it should be given the noisy signals that you get here. This will converge as the radius 1 million converges to infinity to the optimal thing that you can do. Okay. That's the result. Okay. So that's result number 1. Since I'm running out of time, obviously, let me just say quickly what are result number 2 and 3, which should be pretty obvious. So 2 and 3, I'll just draw the model. So in models 2 and 3, the model is the following. In model 2, it's exactly the same. Just let me magnify it, except that for every node, when I zoom out, I also give you noisy signal about V. So I'm telling you sigma V is probably equal to plus. Sigma V is probably equal to minus. So now there's local information to begin with. I'm Facebook, and I know who is likely to be male or female, because maybe what people declare on Facebook is correlated with the truth. And now I want to do something with this information and actually cluster the males and the females. And it says that the local algorithms are optimal in the regime that we're looking at. And model number 3 is similar, except now the degrees are not the same in the two clusters. So all the side information that you get is maybe that the nodes on these sides have larger degree than the nodes on these sides. Okay? So in all of the situation, this result about this very quite delicate process on the tree tell you the optimality of local algorithms of recovering things in these block models. So let me not rush and ask if you have questions before I rush again.
What about your question? Is it always true?
Say again?
Never answer the question, is it always
We don't know. So that's an open problem. And let me say some caveats. If you have more clusters than 2 clusters, so I mean, always just means, I mean, the experts are unhappy, so always just means for the binary symmetric channels, so 2 clusters of the same size. Once you have more than 2 clusters, we know for the experts, there's, in order to have even robust reconstruction to succeed with any noise, you have to get to the Kesten-Stigom bound, and the other bound is irrelevant, right? So you can only look at models where the Kesten-Stigom bound is tight. So we're only restricting ourselves to the case of binary symmetric channel or 2 clusters of the same size. So that's the always that I'm talking about. Lenka, you still seem unhappy.
Some constraint satisfaction problem where this robust reconstruction is not the same as the normal reconstruction, like SORSAT. If have everything is either implied, but as long as I make some errors, I figured everything.
I'm not even color, right? Even if you look at Potts model or coloring.
SORSAT on bounded degree, at least for bigger than 3.
Yeah.
Then the boundary will just always, and large enough, then the boundary will just imply the root because it's
sure.
Like,
Yeah.
But if you make an infinitesimal fraction of errors, you will just not have any information about
right.
it.
Yeah, so this is one example. So there are many examples like that, right? So I mean, this is not the only example. So always just meant, I mean, I'm only looking at the binary symmetric channel. The only thing is that I don't want to restrict the parameters in any way. Maybe it's true for every epsilon. Say in example number 1. It doesn't have to be the case that d times 1 minus 2 epsilon squared has to be bigger than 1,000. Maybe it's true for every value of epsilon. So it's not about other constraint satisfaction problem. It's just for 2 clusters of the same size, but we want it for all parameters. So it's good. The experts are asking questions, so few people are following, so that's good. Let me switch gears and tell you about, I think, a very interesting part. So now, after you went to sleep again, let me just mention something related in the block models, which I think is a very nice problem, which I don't know if anybody studied before, and this would also bring us to the second optimistic prediction from physics, which actually Lenka is behind this optimistic prediction. So let me just ask the question. Which, if some of you have seen before in some context, it'd be very interesting to see what if it was studied. The question is the following. So if it sounds a little too general, question, how well can polynomial time deterministic algorithms approximate calculation probabilities? It's a question about deterministic counting versus randomized counting. So the example can be the following. Maybe I have a graph G, and I have S here, and I have T here, and I want to know that I look at some graph GVE, and I look at a random graph, so E prime subset E is random, so E is in E prime independently with probability P. And I want to know what's the probability that S is connected to T. So of course, with a randomized algorithm, this is trivial. I run a simulation, I do it enough time, I use concentration, and I have a very good answer to this probability. But now I want to insist that there's a deterministic algorithm that does that. That's an example of one question. Example for another question might be, what's the probability that there exists a cluster of size C times n. So that's another deterministic question that I can ask when I do this percolation or when I do this when I look at this random graph problem. And one of the, one interesting prediction that was made is that. So who was the first author? Carrel. Lenka, so I'll write L, even though we know that's not her last name. Okay, I'll write Z. And I don't know if that's the order of the authors, but this. So one prediction was that for tree-like graphs, PC is determined. There is actually a deterministic algorithm. So let me write it as two different conjecture. One conjecture is that it's the second eigenvalue of the non-backtracking matrix. First eigenvalue, the non-backtracking matrix, the -1, I guess. And the other conjecture is that you can compute it with BP. And we know that this conjecture, I mean, this is following discussion with Lenka and with Nike and with maybe other people. We know that this conjecture is not true. I also suspect that this conjecture is not true. Because if this conjecture is true, this would give an answer to my question in a specific case, because it would say that in this specific case, belief propagation can actually compute what's the percolation probability, maybe for this problem, or maybe for that problem. My suspicion is that the answer to this question is also no, and I think in general, these questions about deterministic counting, so it's been done in other areas in computer science, like constraint satisfaction problem. I haven't seen it done so much in questions that come from percolation, and I think it's a pretty natural question to ask. Okay, so I'll stop here and let you get coffee.
Thank you very much, Alkanan. Any more questions, comments?
Yes, Chris.
So, I mean, I think you almost said this, or I sort of assumed it might be in the back of your mind, but so I'll say it. I mean, so the belief is that both when there's side information and when there's any difference in the degrees of the two groups, that the second order phase transition just gets smoothed out, and that it's really a smooth curve, probably an analytic curve even, in which case, if we knew it was analytic, which of course we don't, then the fact that you've shown these two things are equal in one range means it would be equal everywhere.
So yes, so sorry, because I was using a whiteboard talk, I did mention all the work in physics that people do, including Chris and others, but there's some relation which I should actually catch Chris so he explain it to me better again. I think this conjectures about optimality of this local algorithm is related to the or the smoothness of the phase transition. I mean, for me, it's harder to digest, especially after lunch, but it sounds reasonable. So, I mean, it is consistent with the physics pictures that in the case of two clusters, the phase transition should be smooth. And the physics papers, including papers by a lot of the people sitting here, say that in the two clusters of the same size, everything should be smooth. And again, the behavior might be very, very different once we look at more clusters, right? So that's the picture from the physics point of view. Thank you, Chris. Yeah.
Any more questions? Okay, well, thank you very much.